I'm overwhelmed with the amount of information that's been dispensed today, and we've covered it all from stem to stern, the systems, the hardware, the components, the engineering, everything. We're ready to deliver the boat, right? We're ready to deliver. Now, how's she gonna float? And it's all about the ride. To tell us all about that is Bruce Angel from Hatteras. He's Executive Vice President, Chief Design and Technology Officer. He joined Hatteras as a mechanical engineer in 1979. 37 years of marine industry experience, recipient of 6 marine-related patents. And his career responsibilities outside of engineering design have included operations, service, construction management, quality assurance, control, and facilities engineering. He'll be followed by Brooks Stevens, Seakeeper. Brooks began his career in the marine industry in 2001 after graduating from Frostburg State University. Stevens took on purchasing role at Boaters World Marine Center's corporate headquarters in Beltsville, Maryland. Stevens moved on to become inside sales coordinator with Seakeeper based in Southern Maryland. Since 2008, Seakeeper has shipped over 3,000 gyroscopic stabilization systems for vessels from 30 feet to 65 meters. He's currently manages sales for Seakeeper in the Mid-Atlantic, Northeast, and Great Lakes regions. We welcome him here, and we're going to start with Bruce Angel. Bruce?
Good afternoon. Can you hear me? I'd like to thank Mr. Flannery here and Tom George for making this opportunity for me to get here and talk a little bit about Hatteras and also some of the things that we've been doing over the years. And we'll try to squeeze a little bit of the hull form and the naval architecture in there, but hopefully we can provide some additional excitement of some of the things that we've done. A lot of it's technology oriented. The majority of it's scar tissue that we've acquired over the years from doing it this way or that. So get started here. Of course, it all started for Hatteras back in 1959 with nitwits. How many of you had a chance to see nitwits at some of the events? You know, nitwits has got an interesting history. Back in 1984, Dave Parker, our president, decided to go after and try to find it for our 25th anniversary. And of course, back then in 1959, 1960, there was no such thing as HIN numbers. So the question came up, how in the world are we going to find it? And so we had, there was a young guy in our organization, some of you probably knew, Curly Cook. Curly was a 16-year-old kid that Willis Slane hired off of the streets of High Point, North Carolina to work in the plant. And Curly screwed up one day by boring too large of a hole in one of the stud walls. And so Willis Slane got onto him and made him put a patch repair on it. Well, Curly told Dave Park at the time, if I can get to the boat and it hasn't been modified, I'll be able to tell if it's the real thing. So, of course, when people found out worldwide that Hatteras was looking for hull 1 and no HIN, everybody had hull 1. Everybody said, I've got it. So Curly would go to these boats. Some of them had been modified, so that was a little dangerous because, you know, you didn't know if it was a boat. He found the boat down in Panama. A guy by the name of Ted Albrighton owned it, and Curly asked him, said, can I take that panel down on the starboard side? And the guy said, sure, but why do you want to take the thing down? He took the panel off, and of course, that scab that he put on in 1959 was there. So he called Dave Parker up, and the rest is history, brought it back to the factory, and she's been refurbished 3 times. So from an innovation standpoint in hull, that's where it all started for Hatteras Yachts. Now, of course, we've been known, some of you out there know a little bit about Hatteras' past and some of the propulsive technologies that we've utilized over the years. This is an example of some of that technology. Listening to Rich and George and all these guys this morning, I was getting a nervous twitch every once in a while because I've experienced all of that bad stuff that they talked about. But the vibration was a big issue for us because we had an established vibration standard back in the early 70s, but the maximum horsepower was probably 450 horsepower at the time. We still have that same standard today, but those horsepowers are up around 2,600 horsepower. So in order to keep that vibration that Rich talked about at bay, we've had to go to multiple bladed propellers, hybrid propellers, highly skewed blades, you name it. We've had to throw everything in the technological book at these boats to try to minimize and mitigate the vibration and noise issues. This is some of the work that we typically do in getting a propeller developed, whether it's with Rolla, whether it's with Michigan wheel, or even Veeams. We let them go through a comprehensive cavitation analysis to try to minimize the cavitation. By minimizing the cavitation, you're able to remove the noise, and also you're able to improve the performance. Here again is an analysis we've gone through in trying to take a propeller blade and add skew to it, as you can see right here. This actually helps with the vibration that we experience on the boats. How many of you heard of Veeams propellers and the little plastic strips? What do those little plastic strips do? Well, we use the Veeams propellers from time to time, but what we found is that they're very creative in the method they use to try to balance the loads between engines. Most engine manufacturers are plus or minus 3%, but with all the digital information that we give customers today, they will hit us pretty hard wanting to know why one engine's 10 RPM more than the other. This little strip allows us to balance that. So either we utilize the Veeams propeller with a customer preference and they're able to balance the load with the engine, or with other type of propeller, the conventional Michigan or Rolla, will actually bend the tips, very much like you modify the ailerons by controlling an airplane. We don't get down into the root to bend these, we simply bend the tip. So that way you're not breaking the grain structure of that propeller up by doing that. This gives you a little idea of what the difference between a conventional propeller and a Veeams propeller. And this is not pushing one product over the other. It's just that in order to give you that flexibility with a Veeams propeller and using those little plastic strips, the blade has to be much thicker to be able to accommodate that. The key to performance with a propeller is making it as thin as possible. Technically, we can't make it thin enough, but you can see the difference between the two products in terms of the performance, speed, and the vibration. Another problem we have, Rich mentioned the vibration problem he had where he had to change the shaft diameter or shaft length or shaft material. Over the years, we've found that shaft breakage has been a major problem for us. And typically, you would think having 5-to-1 safety factor on a shaft or 10-to-1, as the Cummings guys mentioned this morning, would be adequate. But the problem with that is when you're calculating what that safety factor is, I need to back this up a minute. When you're calculating the safety, well, experiencing, I guess I have to have my problem too. Okay? When calculating the shaft diameter for these boats, we're only calculating the diameter. It doesn't take into account the keyway and all those stresses. And because of the material that we have to use in our industry, this is what they call an austenitic stainless. It means you can't heat treat it to get the toughness that you need. You have to cold work it, like in a forging process. So what that does is it puts a very hard shell on the outside, and as you get towards the core, it makes it softer. It's where the shaft gets its strength and its toughness. The problem with that is these stress risers, where we're cutting the keyway here, well, it's going to do it anyway, so. We've gone to what's called a cylindrical key. And what you see down here below is a finite element analysis that we've done. If you looked at that same analysis with a conventional square cut key, that entire sled runner would be very red, which would indicate very high stresses. By going to this cylindrical key, which we not only cut into the shafts, but we broach the propellers also, we've been able to reduce most of the shaft breakages over a long period of time by as much as 98%. Doesn't mean that we don't have some show up from time to time, but this has been a major stress relief for the shafts on the boats. Here's another shot of the finite element analysis that we conduct on our shafting. One of the shots that someone showed earlier today showed a bearing, and I recognize this bearing from that shot. How many of you have had experienced what they call shaft squeal or propeller sing? Okay? It's hard to get rid of sometimes. Well, a lot of times it is the propeller sing that you can chisel the edges of the blade to take care of that, but in most cases it's going to be the cutlass bearing. And if you'll notice in this area right here, it has the typical slots that run parallel with the shaft line, but it has these other cuts. We call this a waffle cut bearing. So all of the cutless bearings that we installed, this waffle cut pattern is cut in there because when these bearings are positioned in the strut, they're positioned in a random manner. They throw them in, they put the two locking screws in. Well, if the combined weight of the shaft and the propeller is sufficient enough and it lands on one of those flats, what happens is it squeezes all of the lubricating water out of the way and you get that high frequency squeal. If you could literally go to that boat and dial that bearing to where one of those longitudinal slots were, it would wet that specific spot and would take care of the squeal. By cutting these waffle cut pattern in there, we're able to provide water to the shaft regardless of what position it is radially 360 degrees. So you might keep that in mind as you get one of those problem boats that's got a bearing squeal. You can actually install these and it'll take care of that. How many ever heard of a prop smith? Okay. Prop smith, we developed at Hatteras probably about 20 years ago. The main problem being we could not force the propeller onto the propeller shaft tight enough. We're machining a shaft from one supplier. We're buying a propeller that typically the propeller delivery is already late, so they're actually boring that propeller. It's still warm from coming out of the sand casting. So you get a lot of distortion. So you've probably been in yards before where they've blued the shaft, put the propeller on it, and you notice that you get about 25% surface contact. Well, because the shaft is not locked into a clutch like you would in a manual transmission in an automobile, you can easily turn this unless you have the engine cranked. Of course, you can't do that. So here you've paid about $20,000 for one of these exotic hybrid 8-bladed propellers, and the first thing you see a yard doing, they're putting a stump under one of the blades and they got a guy on a 6-foot pipe wrench jumping up and down on it trying to tighten the nut. He'll never get that nut tight enough or stress it to the point where you can get adequate torque. Because you're looking at probably 300 foot-pounds possibly that would need to adequately push that propeller up on that shaft. We developed this in order to be able to do just that. These prop smiths have the capability of pressing that propeller on with about 100,000 pounds of force. And what that does, it actually will stretch the hub of the propeller and allow it to fit onto the shaft, and it minimizes any shaft breakages later on. It also can be flipped over 180 degrees, and you literally can be used to pull the propeller off. So I think most of the dive shops here in South Florida all have these kits, and we also install these on all of the boats. So this has also helped in minimizing the amount of shaft breakages we've experienced over the years. Now, I'm back to cavitation again. What's the difference between cavitation and ventilation? Well, one's not a dental condition. What's the other? Prop slip? Okay, that can come from. Well, cavitation is when you subject the water to such suction that the water will boil. And when it starts to boil, when that bubble collapses, it collapses with such a force, because this is only like 3 milliseconds of time that cavitation bubble forms and collapses. We all know what the result is. If it collapses on the propeller blade, it starts eroding material. Now you might think, how can a bubble erode that kind of material? Well, that bubble, when it collapses, you've got a bubble and it collapses, there's about 1,000 PSI of force in that bubble when those walls of water come crashing in. And if that bubble happens to be on any hard surface, it'll start eroding the material away microscopically, and you get the cavitation burn that we all know of. The cavitation that we typically experience, we typically try to design the propeller so that that cavitation bubble implodes off of the blade and not on the blade. You've all backed down on a fish, possibly, or even with a motor yacht. You hear that rough, gravelly, cracking, popping sound? Well, that's cavitation, because that propeller, it's designed to go forward and maximize the performance you can get. They're nearly not designed to purposely back down, but it is a function they have to accommodate. So that popping and cracking is the noise, that noise you hear is from the cavitation. It's all of those bubbles basically imploding, and you got these little 1,000 PSI pulses. And because water's about 800 times more dense than air, that shock wave makes it right into the hull bottom, and that's where you get a lot of the noise and vibration, which takes me to the next slide. Now, you've seen propellers that I showed before that has that vortex coming off of the tips. That's something that we have not been able to totally prevent in our industry. And because of that, we have to deal with it. Now, the Navy, because they've got an infinite supply of cash, especially going to get a pay raise on the 15th of this month, they can put all sorts of technologies into it. On the nuclear subfleets, they actually have small holes that are bored in the tip of the propeller blades, and they pump air out of those holes in order to fill that cavitation bubble that I talked about that's wanting to collapse. As soon as you take the suction pressure off, they fill it with air, so it allows them to run silent. We took that concept and developed a patented system we call air induction. Now, some of you old-timers have been around for a long time. You've probably seen something of this on 65 Hatterses back in the late 80s and early 90s. What this does, that cavitation popping and cracking that you hear, we actually put a sheet of air. So as the boat gets up on plane and the water's coming down the tunnel, it hits a wedge here, which puts a negative pressure in behind it. As the boat gets on plane and these pipes open up to atmospheric, air is sucked in, and it's evenly distributed amongst inside of that tunnel. And by doing that, we're able to put a sheet of air between the propeller tip, that cavitation, that 1,000 PSI little bomb going off. We're able to insulate that, and that shock wave can't make its way into the bottom of the boat. So we're able to reduce not only the vibration, but the noise that comes into the boat with this patented device. Something else we've done, and we've done a lot of testing at Stevens Institute up in Hoboken, New Jersey, Davidson Labs. We've done quite a bit of testing with tunnels and propellers and hull forms and such. This particular piece of information is a tunnel that we've designed. Typically, this inflow that you want to go into a tunnel, you want to be as subtle and smooth as possible. We sacrifice a small amount of speed, maybe 3 to 4/10 of a knot, by actually designing a ramp right here. What that does in backing down on a fish, you've probably seen those videos of people backing down on a large fish and there's green water coming over the top of the coaming and such. This keeps the stern elevated by providing this vector. So as the propeller is pulling water in here, it hits this plate, and you get a vertical lift component here instead of this angle being more flat with the subtleness, and it allows to keep the transom elevated, and you can back down on the fish much harder than you normally would under normal circumstances. Now we're going to get into hull form a little bit. What are the advantages of a concave hull? Anybody tell me? This shape here. Less pounding? Anybody else? Well, that particular shape right there is what you would have found on Nitwits. It was designed by Jack Hargrave back in '59, heavily influenced by John Rybovich also. And that hull form right there provides you one of the best sea-keeping boat hull forms out there. As long as you're going head to sea, it'll slice right through it and peel it off. The minute you have to go courting sea, this will pound your brains out. Okay? An example would be standing in a swimming pool and taking your hand like this and slamming it in the water. We all know what it's going to feel like. It's going to feel like 1,000 needles sticking in your hand. This is convexity that we utilize on most of our hulls. Most of our competition's doing the same thing now, which is one of the biggest compliments we could get. This is a bell section. So the difference between the concave and the convex is simply, you can also stand in that pool of water and take your hand and do it in this direction and slam it down, and it doesn't sting nearly as much. The reason for that is The convex hull is like taking a basketball and slam it in the water. Over time, as it starts penetrating, a different area is being exposed with it as that movement, whereas the concave hull impacts all at once. So you have to put additional structure in the boat to handle that. And also another benefit of the convexity is you're able to put larger accommodations in internally, and you're able to hold more fuel. Now, there's always compromises. A concave hull is typically one of the driest boats out there. So in order to be able to utilize the convexity, we have to put spray rails on it to try to mitigate the wetness. So that's one of the compromises we deal with from time to time. This is some computational fluid dynamics work that we do on a lot of the models. You see here is our GT60. We start at 14 knots. Now the colors here, the important colors to look at are going to be the red and the blue. And as you see 14 knots, not much is going on. As we start getting faster, you start seeing a little bit of red to start to form up in the bow area. And you also see that right here, you're starting to see the negative pressure due to the propeller sucking water into that. We start getting up to 30 knots. The red is indicating high pressure. So let's just say on a 40-knot boat, at the stagnation line, which is this right here, which is really what provides all of the stability to a planing vessel. What do you think the pressure is, let's say at 30 knots on a boat running there at that stagnation or that chevron stripe? Anybody want to make a stab at it? Okay, I heard significant. Anybody want to give me an insignificant? How much? What would you say if I told you it's only 17 PSI? That's about all we're looking at there. We go to 34 knots. You still see that building. The boat, typically, if we had a speed trim curve here, we'd see it starting to flatten out. Therefore, the pressures would be diminishing somewhat. You can see the discharge of the propeller here, very high pressure. Go to 38 knots. Starting to flatten out quite a bit. We hit to 40 knots, 42 knots. Now, how much pressure do you think we're seeing at the stagnation line at 42 knots? It's not linear. We're looking at only about 32 PSI. And very quickly, as we move aft, the average in that hull form aft averages about 2 PSI. Just unheard of, but it's really, that's all it is, about 2 PSI that you're seeing aft of that stagnation line. So once again, all the stability is typically done here. How many of you heard in your career about the boat keel walks? Okay? Well, there's no such thing, but I've experienced going all over the world with Poulan chainsaws and cutting keels off 46 convertibles and didn't do anything at all in fixing them. The reason for this analysis, let me back up here a minute. The reason for this particular analysis, back up one more time, was because we had a negative pressure that existed right in this area here. And what happened is because, how many of you have taken a spoon and held it up against the flow of water coming out of the faucet in your kitchen? How it'll pull the spoon into it? Well, the bottom of these boats, as we put a convex hull shape in it, that shape in order to get a ride quality. But one of the downsides, you have to be careful with that, as you submerge that rounded shape into the water, it becomes an inverted airplane wing. And we all know what the purpose of an airplane wing is. It's simply to lift the boat. Turn that over, put a fluid that's 800 times more dense than the air, and it literally will suck the boat over to one side. And if you're lucky, it'll oscillate back and forth. If you're not, it lies over to one side, and that's where you get the so-called keel walk. So it all happens right up here in this area. And one of the simple fixes for this, if you know exactly where the low pressure is, you can put a through hull there and vent it to the hull side. The problem will go away. I didn't read that in a book. That's 13 stitches on my left thigh. And or you can put a strip of wood or fiberglass there to simply let that flow that's going down the stagnation line hit that, And what it does, it raises the pressure from a negative 2 psi to approximately 30 psi. And when you do that, the boat will lock up and be solid as a brick. So some of those, so when you're trying to sell one of these older boats and somebody starts talking about keel walk, there is a fix. It's a simple fix. You just got to know where to put the stick. And when I say the stick, you're talking a 1x1 batten is all it takes. It doesn't take much at all. Some more things that we're doing. How many of you heard of interceptors? Trim tabs. It's one of those things that have kind of becoming into vogue here in the last 10 years or so. It's so simple, and I'm so frustrated at all the physics classes and everything else that I did that it didn't stumble on to me that, wow, you've always heard in your physics class or science class, you know, high velocity, low pressure, low velocity, high pressure. Well, when you've got that velocity coming down that hull bottom and it hits this, it's just kind of some very nice laminar flow. But when you got an interceptor here and that flow's coming down that hull bottom and all of a sudden it hits that abrupt stop, that velocity goes to zero and you get a pressure gradient that lifts the boat with very little work. So we're now trying to incorporate interceptors into all of our boats now just because of the effectiveness. And as you also know, these interceptors are fairly expensive. So we've tried to basically utilize a Bennett trim tab hydraulic system and designed our own system, and this is off of our 70 GT right now. Has the same effect. The only difference is this area right here where the interceptor is truly 90 degrees to the hull bottom. We're swinging a little bit of an arc, so we're going to probably be 85 degrees to 95 as we swing our arc pivoting off of the hull bottom. Now, one of the interesting things we've been able to do with this, and I hope Brooke doesn't get upset with me here, I'm showing a fin, okay? Brooke, don't hold it against me, but some of our larger boats have fins. We also use the Seakeepers also, and they've been very effective. But what we've been able to do over the last year and a lot of testing that we've been doing has been with the stabilizer fins that have been pretty common over the years. We've been able to change the angle of attack of those fins and raise the running angle of a boat. This one here happens to be some test work we did on the 70 and the 100 motor yacht. And what we do is we raise the bow of the boat from about 5 degrees running angle along the buttocks to about 7 degrees. And as soon as we do that, we see an increase in fuel burn, we see the boat slow down, and we see a loss of RPM. All a bad thing. But because of the effectiveness of these these interceptors, we're able to put an interceptor on this boat. And you can see here that we got 6% increase in range. Now we're talking a 300 and some thousand pound 100 motor yacht here. And we also saw a average 3.5% increase in speed. And all we're doing is we're lifting the bow and then turning right around and lifting the stern. So it's like the heave value, which is the level in which the boat is out of the water. It's like we're fooling the boat into thinking it's running in a much lighter displacement. We've run tests on boats that are 30 to 40 knots, and we've also run tests on boats that are 20 to 23. So this is a new technology that we're playing with now. We're trying to take this down the path of the fins being small enough that they don't extract any performance from the boat, but effective enough that we can get this benefit. So Brooke, you can still put a Seakeeper on the boat. Something else that patented device we've got, how many of you understand how the differential in a car works? You put your car into a turn, the outboard tire has to turn a greater speed than the inboard tire because that circumference is greater. That makes sense? Well, the same thing applies to boats. When you throw a boat into the turn, the outboard rudder sees a higher velocity than the inboard rudder. And so we have a little term at Hatteras when we test these boats that whenever you throw it into a turn and the angle of attack is great enough and the velocity is great enough, the rudder will stall. And when it stalls, the boat does what we call a crazy Ivan. It diagonally stuffs the bow, and you probably have all experienced that from time to time. And it's generally due to that outboard rudder blowing out. One of the ways we've been able to mitigate that is we've developed this dog-leg tiller arm. So the boat sitting at idle, we have the typical toe end that you would expect to see. But as you see here, in a turning you see the 38.9 degree versus the 40, I think it's 45 there. So we're able to minimize the outboard rudder angle of attack, which therefore makes the stall opportunity go away. And we're able to maximize the angle of attack on the inboard rudder, because not only is it the angle of attack, the velocity going across that rudder slower, it's actually submerged deeper also because it's on the inboard of the turn. So this way we're able to minimize the blowing out or the ventilation of the rudders, which typically is a result of putting deep tunnels in, which we do on most of our boats to try to minimize the draft. This is another view. You can see the difference in angle with the dead ahead. You see the greater angle of attack of this rudder versus the other. We also build our stainless steel rudders. You might ask, why stainless instead of bronze? Well, bronze is a wonderful material from a standpoint of corrosion resistance, but bronze is only half as stiff as steel. So this allows us to use smaller shaft diameters, which provides less drag on the boat. These shafts that we use right here are the aqualloy, the same shaft material that we use in the shafting. There's a keyway cut around the entire perimeter of this, and then a slot is cut into this 3/16 stainless plate. So the weld is simply there to hold those two items together. It's keyed, and we're able to minimize the stresses. Something else that we do, and from a standpoint of trying to improve the seakeeping of the boat, is we pull most of the combustion air on all of our GTs from underneath the gunnels. So that way we're able to move the forward engine room bulkheads further aft, give the customer more accommodations, and with the tunnels and the ability it allows us to flatten the shaft lines out with bigger propellers, we can actually push the engines further aft also. All of that space that typically is eaten up outboard of your engines for the big air boxes, we just let the design and the location of this take care of it. So all of the combustion air goes in through the coaming and through an opening in the aft bulkhead. That way we can utilize all of that area outboard of the engines for equipment and pull the forward engine room bulkhead aft. Structural design. We do finite element analysis on a lot of the structure. We do a lot of tank testing with models. The computer models today are sophisticated enough that the predictions they provide are almost perfect. I still go to Stevens every once in a while just thinking it's going to be the day that I'm able to lift that magic stone and have the new design, but it hasn't happened in 37 years. But this is some of the work that we do to try to optimize the weight distribution and for the performance. Our resins, a skin coat on our boats. Although all of our hulls now are resin infused, we do put a pure vinyl ester skin coat on to help blister guard protection. It also provides a barrier to the mold to provide better cosmetics once we do infuse. It's very difficult to infuse a product today and get a gel coat finish out of that. And of course, all of the infused resin is a blended polyester and vinyl ester, reduces shrinkage and provides us with better cosmetics. The tanks are still fire retardant resin, and of course FDA approved resins for the potable water systems. We use quite a bit of core. I wish I could say that we'd never use balsa core in our boats, but in 1984-85 we stopped using balsa. It was just such a challenge. It has wonderful physical properties. The only downside is it rots, and so you never know what's going to happen with the guy on the production line. Is he going to put a screw someplace and decide he needs to pull it out and not caulk it? So the water intrusion can be a major problem. So we use all of the PVC foam cores, and because we are infusing the boats, all of that kerf cut gets filled with resin, so we don't have to worry about any water intrusion at all. Advantages are stiffness, reduced weight, and optimum glass to resin ratio. Typically in a hand lay in any factory, the hand lay, you're very lucky if you can get a 50-50 glass to resin ratio. Most of ours at hand lay were 60% resin, 40% glass. Glass is where the strength comes from. The resin's simply a binder. By going to resin infusion, we're able to raise that and flip those ratios. The glass goes to 60% and the resin to 40%. So we're able to increase the stiffness and the strength of all of our laminate just by going to the infusion process. And of course, we're using a patented closed mold process that we didn't develop, but we're utilizing it. And we use vacuum pressure to distribute the resin. How many of you have ever seen an infusion process? Kind of interesting, isn't it? This is one of our GTs being infused. The fusion has just started here. If you notice, this is very dark right here. We're starting to bring fluid in, and it's starting to saturate from the keel up. And as it progresses, it makes its way up the hull side. Typically, there's no time saving at all in infusing the hulls. It takes the same amount of time to load all of the dry glass and all of the foam. We draw straws to see who the guy's going to be to launch the space shuttle, because that's what it's like, because once you start this thing, you can't stop it. But it takes about anywhere from 2 to 5 hours to totally saturate it. And once we start venting and getting resin at the shear line, we shut the valves off and we wait for it to cure. Once again, we use the foam cores on the hull sides. We run foam all the way down to the running chine because we are filling that kerf cut with resin. We're not concerned with the static displacement of the boats. So from the upper chine to the lower chine, the foam is exposed to water, but because of all the kerf cuts are filled with resin, we don't have to worry about any water intrusion. We utilize UL Marine approved tanks. We also utilize integral tanks. Something like our 63 has one tank. It's on center line. It's right at the CG of the boat. So as you burn the fuel off of that, you don't have a trim issue. You're not constantly on the tab. So the boat comes right up, the heave value. You're able to maintain that running attitude without screwing with the tabs, and also take advantage of the weight as you burn the fuel off. Took a little while for me to get used to pouring fuel in the bilge, but I got over it. Here's a shot of one of the integral tanks. We're able to reduce the laminate somewhat because the baffles that we install in these tanks end up being a structural component. And they're water jet cut on our water jet mill and for an adequate fit to the hull bottom. Therefore, we're able to get the panel sizes smaller and able to improve the stiffness. And that's it. Any questions? No. How do I do on time?
I have one question.
Yes.
On your vinyl ester resin versus the polyester, what is the difference in the two? Or why
The
would you use vinyl
elongation.
through the entire boat?
The elongation. Typically, the vinyl ester resins are more flexible. They're not as brittle, so they give us better elongation.
And then on one other thing is when you do the infusion and you have all the excess resin, I guess creates a lot of weight. How do they remove that? Do they have like vacuums, or the guys get in there and scrape that?
Well, no, because you're saturating, you're pulling a vacuum on a vacuum bag, you're able to reduce the resin from the 60% on the hand weight to only 40%. But all of those tubes that you saw, they're full resin. So for every shoot we do, we average about $5,000 to $6,000 of expendables that just have to go to the landfill because of that extra resin.
Microphone, please.
Simple question, I think. On the larger center consoles that use step hulls, what effect would the step hull have on the faster sport fish boats, and why is that not used?
I would love to use it, but the problem is typically we use what's called a submerged propeller, and if you put a stepped hull on a submerged propeller boat, what would happen is that propeller has such a demand, it would ventilate and create this imaginary trough and totally ventilate that propeller. The reason they're efficient on surface piercing is the top 2 quadrants of the surface piercing propeller are ventilated anyway, so we're able to tolerate that. And I wish I could slay that dragon, but that's the main reason. It would just totally ventilate the propeller. Now, the air induction system I'm talking about, you know, like any good engineer, if he runs the boat and it worked, he's going to double it and say it'll be twice as good. Well, when I did that with that air induction system, we did exactly that. It ventilated the propeller, and those propellers, once it opens that trough up, it'll pull anything in underneath the boat. But from a resistance standpoint, if you could get rid of that issue, it would definitely reduce the resistance of the boat, and it'd probably be on a 40-knot boat worth at least 3 to 4 knots.
Okay, I need to get Brooke from Seakeeper up here, and if you could hold your questions, maybe till the very end, maybe you can readdress them with Bruce. Brooke?